Welcome back. Today, we are going to dive into the fascinating world of functions, one of the most important ideas in mathematics. You can think of a function like a machine or a rule. When you feed in a number, which we call the input, the machine processes it and gives you exactly one output. In more precise terms, a function is a special kind of relation. Here's the rule. Every element of the domain has exactly one image in the codomain. Every input from the domain is connected to one and only one output in the codomain. This is what makes functions so powerful. They help us model real-life situations like predicting profits in a business or tracking how temperatures rise and fall over time. In this lesson, we'll explore some of the most important types of functions you need to know and see how each one looks and behaves. Let's begin with two of the simplest types of functions, the identity function and a constant function. First, the identity function. Mathematical expression f of x equals x. This means whatever input you give, you get exactly the same output. If you input the number 3, the output is also 3. Graphically, it's a straight line that passes through the origin and rises diagonally at a 45-degree angle. Second, the constant function. Mathematical expression f of x equals c, where c is any fixed number or constant. In this function, no matter what input you use, the output always stays the same. For example, mathematical expression f of x equals 4. The graph of this function is a horizontal line crossing the y-axis at y equals 4. These two functions are important building blocks in mathematics. One simply returns your input, while the other completely ignores it and gives you a fixed value every time. Now let's move on to some more complex and interesting functions that you'll see often in mathematics. First, let's look at polynomial functions. Mathematical expression f of x equals x squared. This is called a quadratic function, and its graph is a smooth parabola that opens upward. Next, let's look at rational functions. These are formed by dividing one polynomial by another. Mathematical expression f of x equals p of x divided by q of x, where q of x is not equal to 0. Example: mathematical expression f of x equals 1 divided by x. The graph of this function has two separate curves that get closer and closer to the x-axis and y-axis, but never touch them. These invisible boundaries are called asymptotes. Polynomial and rational functions show up everywhere in science and engineering, making them essential tools for modeling and solving problems. Next, let's explore two important special functions, the modulus function and the signum function. First, the modulus function, which shows the absolute value of any number. Mathematical expression f of x equals the absolute value of x. This function always gives you a non-negative output. For example, the absolute value of positive 3 is 3, and the absolute value of negative 3 is also 3. The graph of this function looks like a V shape, with its sharp point exactly at the origin. Next, the signum function, which tells you whether a number is positive, negative, or 0. Its graph has 3 flat steps. One step above the x-axis for positive numbers, one point right on the axis for 0, and one step below the axis for negative numbers. Together, these two functions are useful for expressing absolute values and detecting the sign of any real number. Finally, let's look at the greatest integer function, a special function that always rounds your input down to the nearest whole number. Mathematical expression f of x equals the greatest integer less than or equal to x. Let's see some examples. If x is 3.7, the greatest integer less than or equal to 3.7 is 3. If x is negative 1.2, the greatest integer less than or equal to negative 1.2 is negative 2. In short, open bracket 3.7 close bracket equals 3, open bracket negative 1.2, close bracket equals negative 2. The graph of this function looks like steps moving horizontally. At every whole number, the graph jumps up to the next step. That's why this function is sometimes called the floor function, because it always takes you down to the floor of the nearest integer. Let's see how we can combine functions to create new ones. When we add two functions, it's written as f plus g of x equals f of x plus g of x. That means we simply add the outputs of the two functions for each input. To subtract, we write f minus g of x equals f of x minus g of x. Here, we subtract the second function's output from the first. Take the example x squared plus 2x. This combination gives us a new curve, a different function altogether. Each time we add or subtract functions, we're not just doing simple arithmetic. We're creating a brand new function with its own unique behavior and graph. Let's explore how scaling and multiplying affect mathematical functions. First, multiplying a function by a number stretches or shrinks its output. For example, 3 times f of x equals 3x. This means the slope of the line becomes steeper. Next, we can also multiply two functions. This is written as f multiplied by g or f times g. It means we multiply the outputs of both functions together to create a new product. Let's look at a simple algebraic example. X multiplied by open bracket x plus 1 close bracket equals x squared plus x. Spelled out, x times the quantity x plus 1 equals x squared plus x. These operations, scaling and multiplying, help us transform and combine functions in powerful ways. Ask ChatGPT. Now let's talk about dividing functions. To divide one function by another, we write f divided by g of x equals f of x divided by g of x. But remember, g of x must not be equal to 0, because division by 0 is undefined. Here's a quick example. X squared divided by x simplifies to x as long as x is not 0. So just like numbers, functions can be added, subtracted, multiplied, and divided. Next, we'll explore advanced functions and their properties, where things get even more interesting.